Hello class, today we shall be studying on the topic packing efficiency in this particular video. So let us first see what is the meaning of packing efficiency. Packing efficiency is the percentage of total space occupied by the particles. Okay. Now before we move on to the next part, I just want you to inform that kindly note down these things in your note copy as well. Okay. So under this packing efficiency, there are different types of arrangements, and for every types of arrangement, the packing efficiency may not always be same. Okay. The first one, that is the cubic close packing or face-centered cubic arrangement. In this type of arrangement, 8 particles are present at the 8 corners of the unit cell and 6 particles are present at the 6 faces of the unit cell. Okay, so let us move on straight to the derivation, that is, okay, to find out the packing efficiency. Okay, let A be the H length. Okay, let A be the H length of the unit cell and R be the radius of each particle or say sphere. Okay, normally we take spherical shape. Okay, so then the next one, okay, the next step is, since it is a face-centered cubic arrangement, we also have to know how many atoms or particles or spheres are present in one unit cell. Okay, so number of spheres in one cubic unit cell, or say in one unit cell, is equal to, I hope you know, it will be 8 into 1 by 8. Okay, for each 8 atoms, I mean 8 particles at the 8 corners of the unit cell. Okay, it shares 1 by 8, okay, of its part to the to one unit cell, and 6 atoms are there, or 6 particles are there, or 6 spheres are there, which will be multiplied by half because it shares only half of its part to one unit cell. Okay, so we get, this one is 1, this one we get as 3. Okay, so total number of spheres present in one unit cell is 4. Okay, kindly note down this one. Okay, now we go to the next step. Okay, that is, we have to know the diagonal length. Okay, because since I mean, in our previous classes and all, we have seen about, or we have dealt with regard to the nearest distance. Okay, so in this case, the nearest distance between any two atoms will be along the diagonal. Okay, along the diagonal of the faces, that is the AC. Okay, so therefore we have to know the value of AC. Okay, so AC is equal to, if we have to write in terms of the radius, in the form of radius, then it will be R plus R, 2R, 2R plus 2R, it will be 4R. Okay, this one you take equation 1. Okay, then again you see in the right angle triangle, in right triangle ABC, by Pythagoras theorem, okay, you have to write in full form. By Pythagoras theorem, kindly remember this one. Okay, there are 4 number of atoms or 4 particles present in one unit cell. So by Pythagoras theorem we get, or we know that it is AC square equals to AB square plus BC square. We are doing this one, okay, the ABC, we are doing this one in order to find out the relationship between the radius and the H length of the unit cell. Okay, so here we write in terms of the H length. Okay, so AB is A and square, BC is also A, so A square, AC square equals to 2A square, then AC will be equal to root over 2A square, which will be root 2A. Okay, so this is the value of AC. Now we put this value of AC in equation 1. Okay, so yeah, putting the value of AC in equation 1 we get. Okay, So root 2a equals to 4r. Okay, then you transfer this root 2 to the other side, it will be 4r by root 2. You can rationalize it, it will be root 2 by root 2, that will be 4 root 2 r divided by 2. So 2 1 are 2, 2 2 are 4. Okay, so what we get is a is equal to 2 root 2 r. Okay, now this is the h length. Okay, this is the h length of the unit cell in terms of radius. Okay, now as you can see, packing efficiency, and here we have to find out of the total space occupied, isn't it? So space means volume. Okay, so that means we have to find out the volumes of the unit cell as well as the volume of the particles. Okay, so I hope you are done. We shall go to the next step. Okay, that is we have to find out the volume. Okay, we have to find out the volume. So volume of unit cell is equal to, okay, we know it is a cube. Okay, this is a cube. Yes, no, it's a cubic structure, so therefore volume of a cube is a cube, and we already got that value of a, that is 2 root 2 a, 2 root 2 r, and cube is there, so like this, since a is equal to 2 root 2 r. Okay, then what we get here, this will be 8 into 2 root 2 r cube, isn't it? So this will result in 8 to us 8 to our 16 root 2 r cube. So this is the value of the volume of the unit cell. Okay, so let me just note it down somewhere here, 16 root 2 r cube. This is the volume of the unit cell. Okay, C for cubic. Okay, I'll just note it down for now. Okay, now I go to the next one. Okay, I have to find out the volume of the particles or the spheres as well. Okay, so since the particles are spherical in shape, so I apply the volume of the sphere formula. Okay, and in the beginning we have found out that in one unit cell there are 4 particles or 4 spheres present, isn't it? So that's why we find out the overall volume of all the 4 spheres. Okay, so volume of 4 spheres is equal to 4 times, okay, the volume of each sphere. So that is, since it is spherical in shape, so it will be 4 by 3 pi r cube. This is a value of, this is a formula. Okay, so 4 are 16 by 3 pi r cube. Okay, this is the value for the volume of 4 spheres. Okay, these two. Now packing efficiency, we have to find out the percentage. Okay, so if I give you just an example, if you're asked to find out the percentage of the particular subject one, then how we do is percentage is equal to percentage of any subject is equal to marks secured by total mark secured by total mark, and we multiply it by 100, isn't it? So mark secured and total mark. So here also we apply that same thing. Packing efficiency is equal to, okay, packing efficiency is equal to, we are asked to find out the packing efficiency of, we will find out the packing efficiency of the particles. So what we do, it will be, just wait. So how we write this, packing efficiency is equal to, how we find out is, since we have to find out the packing efficiency of the particles, so that means the total space occupied by the particles. Okay, so here also what we do is, it will be volume of volume of, according to you, okay, see, volume of, it should be 4 spheres, okay, because it is the particle that is occupying the space of the unit cell, okay, and here the larger area is not the unit cell, I mean not the particles, but it is the unit cell that is having the larger area, okay. And here also, but in finding out about the subjects, total mark is the maximum mark and mark secured is the, okay, lesser mark than that of the total mark. So here also total space is the volume of the unit cell, and the part occupied by the particle is the volume of the 4 spheres, okay. So it will be volume of 4 spheres divided by volume of unit cell, and then we multiply it by 100, okay. So that is it. Then we write here 16 pi r cube by 3 divided by this one, okay, this is the volume of a cube, so that is 16 root 2 r cube into 100. So here we get 16 r cube gone, so it will be 3.14 divided by 3 into 1.414 multiplied by 100, okay. So if we calculate this one, we get around 74 percentage, okay. So that is the packing efficiency for the cubic close packing or face-centered cubic arrangement, okay. I hope you are clear with this one, and I want you to note it down, this one, in your note copy, okay.